People! Thank you, Ryan. That was a pathetic clap, you people. You know, I need a theme song, Neil. You better write me a theme song for this class, right? I'm gonna edit it on here.
For the last one.
Yes, I wanted that. Why did you have to delete it, Neil? I loved it. I'm gonna play on a theme song. We're just gonna dance on top of the camera, right? I know my friend will be watching this one day, so hi. Anyway, I'm gonna have to edit that out. Future David here. I didn't edit it out. On a side note, I'm looking through these recordings, and boy, does my voice sound annoying. Like, how are people gonna watch these? Anyway, back to my annoying voice. So, what are we gonna do today? Well, I'm going to start with jogging your memory, because I know you guys have the memory of a goldfish, which is frankly very offensive to the goldfish. So, I'm going to start off by showing you, actually, let's start off with you showing me what you remember. I'm going to name...
What topic?
This is machine learning, man. We're back to this. I know it's been a while. It's been a while.
Shit. I can't remember the formula.
Okay, don't worry. It's in your booklet. Okay, your formula is in the formula booklet, but I will start by reminding you of the basic things of the dumb, I'm going to call the dumb method. Small tidbit here, it's not that it's dumber per se, it's just better for other uses, as you will see later on. I just thought I'd make that clear now. And then I'm going to show you the better method. Again, better here is relative, okay? And this board feels very high, but anyway. So, we're going to start with, well, our normal cost function. Who remembers the cost function is j of theta is equal to 1 over 2n. Theta, what is that? Up to n, I equals 1 of h theta. Sorry. 1. Okay, that was our square difference cost function. I'm sure you guys remember that somehow. And we went through intuition on why that works and how that works. We'll talk about implementing this, but probably not today. So, I want to introduce you to the idea of what if we have a function that is quadratic rather than our straight linear function that we're trying to fit. So let's say we have something in the form. By the way, we remember that theta is our parameter, and that's what we're going to be changing. We want to change our parameter so that our hypothesis function is going to be equal to our function that we're looking for. So we're just going to call it our f of x function that we're looking for. Now, let's say we have a function that is in terms of, let's say here, we'll go from a theta squared plus b theta plus c. Right? That is a quadratic function, right? So let's say we want to minimize the cost of this. We're going to do minimize over j of theta of that, right? So what can we do? Well, we can do something that's kind of interesting, and actually this is what we did before. We're looking for the points where the derivative is 0, because we're going to be looking for the lowest points on our graph. So turning points, right? You may be familiar with that in calculus. You may have done searching for the points where the derivative is 0. Yeah. So what I'm going to really do is rewrite that and just say, well, d theta of j of theta. And we're going to, whatever that is, we're going to set that, so set to 0. Because we want our derivative term to be 0. Because if our derivative term is 0, then that is what we're going to be finding. We're going to be finding that lowest point, which we want to find because that's the point of our lowest cost, right? Does this make any sense, Neil? You okay with that? Okay, good. Now, I'm going to try and now introduce you to a method that is, actually, well, we have to then, you know what, never mind. There's no point in going on with this method. That method, to do your traditional cost and then iterate through every single time through a loop like we did before, this is kind of computationally intensive, and it becomes annoying for us to even do the math for it. So I'm going to show you a easier way to do this. It's called the computing of parameters analytically. So this is what we call iteratively. So this is the iterative process, which means we go through it over and over and over again. So the iterative. Now, and then we're going to start with the analytical. Okay, the analytical is slightly different, and this is This is where your linear algebra needs to be very good, right? Because this is the fun stuff. This is what is really what we're going to be doing a lot of the time, because we don't want to work in terms of iterative processes unless our data set is massive. We want to work in terms of analytical for small data sets. It allows us to work easier. And I'm going to discuss today some very interesting properties of a special type of matrix inverse. We're going to prove that, and I built a octave program, and it's visual and graphic so that you guys can see what I'm going to be talking about. Okay. So, I need to start with a data set. Side note here, Stanford, please don't sue my ass. I may have taken your data set. I was too lazy to make my own. Please, don't sue me. And so I'm going to take a few minutes, a minute or two, to actually draw the data set, because we're going to be using this data set a lot. I may as well draw it, write it on the board. It's got a ton of things. So we're going to start with x0, x1, x2, x3, x4, and y. So we can just like make a nice table, like so. Also, I hope Stanford doesn't like sue my ass for taking their stuff. Please don't sue me. Anyway, so we got 1, 1, 1, 1. Number 2, 1, 4. It's not necessary for you to copy this. This allows me to just use this for example purposes and explanation. Yes.
Some big numbers.
You see what these mean. I'll explain in a sec. 2, 3, 5, 6, 40, 232, 315, 8. Okay. So what did these mean? So this is, remember we call this our bias? I mean, I think it's called a bias. Don't quote me on that though. We have added a 1 that allows us to do certain matrix multiplications and things. So don't worry, the 1 doesn't really have a value. It's simply what we call the bias unit. After thorough research of about 10 seconds of Googling, I have come to the realization that it's not called a bias unit. That is a similar idea, but however it's being used in neural networks and not in linear regression. I apologize to you and your family. It just allows us to perform certain applications with matrices, because otherwise the dimensions won't fit. So we can't do multiplications. So we have to add the 1 at the beginning. So this is going to be our size of our house, right? So we're going back to our South African house census, right? Size in feet squared, right? Here it's going to be the number of bedrooms.
I see.
You see that what we've done is actually add more features. Yeah. Remember, our x is our features and our theta is our parameters. So we want to calculate, we're going to have a lot more parameters now. So we're going to come up here. This is going to be the number of floors.
So why is the price, right?
That's the price is higher. The number of floors is, well, it's dependent on other things. This is just an example data set, right? The age of the home.
Well, y is what we're looking for, right? So it would be...
we have y, we're looking for our theta. So that our relationship will result in y being the true value, right? So that's going to be the age of the home. And this is going to be our price. So this is our price that we're looking for. We want to find, in essence, calculate some value that we can put in and always get a value that is close to y. That's what our entire job is. Now,
but do you consider all that factors into one equation?
Yeah, that's... Like,
yes, we're going to.
Crazy.
It's going to be easy though, because we're going to do it using matrices. Now this is a process called the minimization through what's it called? Explicit. Come on, man. I really had a brain fart right about that. And explicitly, we're going to do this explicit minimization. I can speak today clearly. See. I'm not worried at all. Anyway, we're going to do this using explicit minimization. So that means that we're going to perform an operation that can do all of our matrix calculations in one go, rather than doing it over and over and over again. We're going to be able to calculate everything. That's the power of matrices. So what we're going to do is we're going to come up with an algorithm. So remember, our old algorithm was called gradient descent. We go down a gradient until we find our gradient to be 0. So that gives us one way of minimizing j. So let's think of a second way of doing this. So this time we're going to perform minimization explicitly, like I said, and without resorting to an iterative algorithm. This is called the normal equation method. So the normal equation method. This is in your data book. It's going to come up with many terms of the normal equation.
But this isn't a quadratic.
We don't actually know this function, and we don't need to know this function. And I'll show you why. The normal I can't spell it. Equation. Right, see, I'm an amazing speller. Shut up. Now, the normal equation method is a way that allows us to perform this, like I said, explicitly. And I would write it down first, but I'm going to come up to some intuition to why this is so. We can turn all of this into a matrix. Now, we're going to turn into two matrices. One is going to be something called our design matrix, and one is going to be our Y matrix, or vector. This will be our final vector. Now, to do that, I could rewrite the numbers, but I'm not going to. So we're going to end up with this being a matrix. So if you remove all of the lines, this is your matrix. This is called the X matrix, or our design matrix, represented by capital X, right? So this is our design matrix. So on one side, we're going to have our ones, do, like so, right? There are many ways of representing this, and I'll show you in a sec how that works. But first, and the Y matrix can then be represented as just simply Y like that, which is a vector. We're just denoting its vectorization. And then we say 4, 6, 0, 2, 3, 2, 3, 1, 5, 1, 7, 8. This is our matrix of Y, this is our matrix of X, which is our design matrix, right? Now, what's the dimension of this matrix though? The dimension of this matrix, no, not the actual number, but the actual dimensions in terms of in kind of like an equation form. This is an M by N plus 1 matrix. And it's not that you really need to know that, but it can come into some importance, but it will always be written down if I have to actually talk about it. So M, remember that M is the number of like examples, and thank you. Now, sorry, this should actually be an M. I realize that now. You can tell I'm incredibly professional. M is the number of training examples that we have, and N is going to be irrelevant. Now, N is I think the number of features that we have, but again, it's not exactly important. Now, N plus 1 or N minus 1? N plus 1, okay. So we're going to talk about the general case. So we're going to have some M number of examples. So this is M is equal to 4 in this example, because you know, M equals 4. Right. So we're going to come up with our general case for this. So general case. A general case. So we're going to have M examples. M examples. And that's where what we're going to say. We're going to have xi, or x1, y1. And what does that mean? Is that we're going to have this row. Right? That's our row. It's going to be the x of one row here for it, just so that we can make it simple. And then this is going to go up to, well, our x m ym. Right, so that we can go so we're going to start with, this is going to be our x1, well technically that's our y1, but just ignore that for a second. That row, and then that will be our x2, x3, and then this will be our xm, because that's our final one. That will be x4. Right? That's what we mean. And we typically represent this as x, right? It's not exponentiation, it's just a value that tells us which row we're in. And by the way, if we want to know which column we're in, which feature we're talking about, it would be like this, x3i or xji. So j is going to be the number here, I is going to be which row. So if it's 3, j is 3, and I is 2, it will be this number that we're talking about. Okay, so just bring me the eraser. Now, Shut up, Ryan. Now, I'm gonna show you here something that we can do that's quite interesting, is that we can create our matrix xi. It doesn't matter what I called it before, Ryan. Well, maybe throw it at you. You laugh now, but I'll throw it at you. Now, we're going to have our xi matrix. Our xi matrix is going to be, well, I'll show you what it is. We're going to have our xi, this is x0, x1, x2, x whatever. Why is there a 1? Okay, x, and then x to the ni, so some number n that you have. And again, remember, this is going to be our matrix. Technically, what I've done is I flipped it this way. Notice how it says xi, so if I is 1, right, if xi is 1, we can just do this, x1, x0 of 1 is 1, x0 of 1, x1 of 1 is 2104, etc. And that goes down like this way, but this way. I've created a column vector in essence, right? And our design matrix, another way of representing our design matrix is actually a matrix of matrices. And we can do this. Again, this isn't that necessary to understand, but I want to get to some intuition where this comes from. So we can represent this as x1 transpose. Again, if we remember what a transpose is, it's going to be our, yeah. And notice how this is, remember I showed you x1, this is xi. So what I've done is if I take xi, transpose it, what am I going to get? I'm going to get this that I started out with. That's going to be, that's a way that I can represent this and easily represent this. So we're going to end up with x2 transpose, x3 transpose, up to xm transpose. Does that make sense? We're all okay with that? Essentially, it's just this. No difference between x and x. These are exactly the same. All I've done is shown it in another way using transposes. Because this allows us to, in essence, just keep each column and then shove each column together.
Wait, a transpose is not like flipping?
It's like
Yes,
this.
it's like taking, if a matrix is like this, flip it like this. If it's like this, flip it like this.
Why is it still in a line?
Because, well, I just wrote the transpose of those.
Yeah.
I've taken the transpose of every individual matrix.
Oh,
I'm
X,
making a
okay.
matrix of those transposes.
Yeah,
Rather than taking the transpose of x. We will have to take the transpose of x eventually, and you'll see why. Now, I have some examples here. But we forgot one thing, though. One thing is missing from, actually, no, this is all fine. This can be written also in another way. There are many notations here for you guys to remember. I hope you understand a little bit of what I'm doing here. If you don't worry that much, because we're not going to need it, because I'm not going to show you tons of proof, and you're not going to have to be able to show proof. That's more my job than yours. So we can represent this as 1, 1, 1, how many ones you need, and then it goes x1, x2, x. Yeah, it's just tons of ways to represent this stuff, but again, not necessary. Now, how did I represent y? It's like this. So how am I going to generalize y? We can generalize y quite simply. We don't need this actually. Just think of it as essentially your data becomes your.
Does the one row equal the y?
Yes, one row is equal to that y. One
Okay.
row is equal to that y. One row
So
is
that's
equal
why
to that
we
y.
do this, right?
Yes, that's why
Okay.
we're going to be doing this.
I see.
Now, what we're going to do is now represent our y. Our y vector. By the way, there's no vector sign in your notes. It's not necessary, but it's always good to show you that it is a vector. But it doesn't always have to be a vector, by the way. We can be calculating multiple things and multiple parameters and final results. But for now, we're going to think of everything as we're only looking for one answer, and that's it. So this can be represented as y, well, 1, y2, up to ym. And that should be intuitively, should make intuitive sense, because this is y1, this is y2, and etc. And this is going to be, of course, ym. Again, this is not exponentiation. I'm going to keep reminding you of that. That is just telling you which row it's in. This is etc. Right? Okay, now I'm going to actually now show you the algorithm. It's one line. So it's one math equation. Very simple.
It probably means a lot, right?
It means a lot, of course. Also, I have to stress that we're going to work with theta. Theta is going to be its own matrix. theta is going to become a matrix of parameters. So let's say we're going to have our theta here. Our theta is going to be some matrix parameters. And that's going to be dependent on the number of parameters, number of, number of features that we have, features, right? So we're going to end up with this theta matrix. And when I write theta from now on, I'm going to be talking about the theta matrix, right? So our theta matrix in this example will be theta 1, theta 1, theta 2, theta 3, theta 4. Yes, it should be theta 4, right? Because the first one is obviously going to be 1. Because if we remember back to our biases, we can remember that, well, this becomes 1 because theta 0 times x0 is 1. Future David here. Correction. Theta 0 itself has a value that isn't 1. It's going to be x0, which has a value of 1. And again, it's not a bias. Just thought I should correct myself. That's why. So it's going to end up something like this. You're going to get theta 1, theta 2, theta 3, theta 4, right? Like this. This is going to be our matrix, and this is going to tell us our thetas. Rather than, remember here, what we did here is we're going to eventually compute each theta individually. Here we're computing all the thetas at once. So we can spit out your value for theta very quickly. Well, quickly, and you'll see why that quickly becomes kind of hard to do after certain values. And well, I'll show you that. I built two programs.
Right, but not the computer.
No, for the computer. There are computational limits to this, and we'll view these computational limits. Well, now since we don't like the iterative algorithm, it's kind of pointless to us. We're gonna
Erase it all.
erase it. It's crap. Now let me show you the normal equation. The normal equation. Also, by the way, does this all make sense, Neil, Brian? Is this all okay?
Yeah, I get it.
Yeah, it's not exactly necessary, but it's always good to know what the heck this thing is even doing. Now, we're going to show you the normal equation. Now, the normal equation is going to be this. Theta, again, theta is our matrix of thetas, is going to be x, which is again our design matrix, transpose, times x normal.
Right, so we're not trying to find the cost anymore? We're just trying to
No,
find
we skipped the cost. We'll get to that. We are skipping cost entirely. We're cutting it out of the equation. Because why should I be looking for cost if I can compute each theta like on its own?
Yeah, this is true.
You'll see in a second what this does, right? It's the minus 1. So we're taking the inverse of this. And then we're going to multiply all of this by, again, x transpose multiplied by 1. That is the fundamental, the normal equation. Very, very important stuff. This thing, you don't need to learn off by heart. I learned it off by heart because it's quite simple. It's a short equation.
Won't the x transpose just cancel itself out?
But no. Remember that matrices don't cancel.
Okay.
What it's doing is I can't multiply x by x. What if x, like here, what is this? X is a 4 by 1, 2, 3, 4, 5 matrix, right? If it's a 4 by 5, if I didn't do the transpose, what would be the dimensions of my other one?
Isn't the inverse just 1 over, like, whatever is there?
Yes.
So then wouldn't they just be like...
No. The inverse, remember our inverse function? That we calculate the inverse of...
Oh, it's for the matrix.
Yeah.
Okay, I get it.
Notice that, well, so let's imagine we have our RT. We can do a bit of intuition for this equation, right? I don't want, this thing is annoying me. You can stay there. Now,
What is that?
I have no idea. I've never been in this classroom before. This is my first time. Now, let's
This thing
imagine,
has always been here.
irrelevant. Now,
You're the first one to take it off.
yes, I've committed a crime. Now, let's imagine that our x, I'm just trying to see, does the camera even see that, like, that side of the
I
root?
think it does, because I see a little, like,
I know.
dark side to the left.
I'll just move it, right, so
So-
that we can see it better, and then remind me to move it back. So let's say the dimensions, right, that x is going to be part of our 4 by 5 matrix, which is going to be this, right? What does that mean? It's part of a matrix of real numbers of dimension 4 by 5. That's just a notation, right? And our y matrix is then going to be part of the what's it going to be? Obviously, it's going to have to be a 4 by 1 because it's going to have to match, right? So what are we going to do is we're going to actually see, we're going to do something called dimensional analysis, and we're going to find out whether or not this even computes at all. And you'll find out that it does, and we'll get back to this part. This is an incredibly important part and some of the most interesting in linear algebra that exists. But first, we're going to start with this. So x to the t, x transpose, right? X transpose is going to become a 5 by 4 because we just flipped, right? And what's multiplied by what's the dimension of x? 4 by 4.
Oh, okay, that's why it works. Okay.
Notice how numbers here. The output is going to be a 5 by 5, right? Right? Is that how?
Yeah, it is.
Yeah. This tells you whether you can multiply them. This tells you whether right.
I remember that fine.
So we see 3 by 1 and multiplying by 1 by 3.
Yeah, and then you get 3 by 3 out.
Yes. Okay. I remember.
It's
Okay.
been too long for all of us.
I know, it's been a while. So now we're going to take the inverse of this, and we're going to see what that does. And then multiplying by x transpose again, that's going to be our 5 by 4. Multiplied by y is a 4 by 1.
And it works.
Yeah, it works. You're going to get a 5 by 1. You can get, you see the 4 by 4 is there. You're going to get by 5 by 1. Now, this is going to result in a 5 by 5 matrix. So we could do this. It's going to be a 5 by 5. By the way, these are just going to be dimensions, nothing else, right? They're not numbers per se. This is going to be a 5 by 1. Now, if we take the inverse of a square, it's still going to be the square, right? So this is still going to be a 5 by 5, and this is going to be a 5 by 1. So what we're going to result in is we're going to have a 5 by 1 matrix. 5x1 matrix. And what does that look like? Well, that's going to, does that make any sense? Well, then you're going to result in theta being
1.
yeah, it makes sense.
Yeah,
1, 2,
yeah.
3, 4, 5. Done. Notice that you're going to end up here, you're going to end up with theta 0, which is 1. Dipshit, it's not 1. So theta 1, theta 2, theta 3, theta 4.
And what does theta mean again?
Theta is a parameter. It's what allow in our equation, for example. Let's try and model this equation. It could be something complicated. I don't exactly know, but let's make it to be like theta 0 x0 plus theta 1 x1 plus theta 2 x2 plus theta.
This is an equation.
Yeah, this is the equation. This is our whatchamacallit. I'll show you in a second what this means. Theta 4 x4, right? This is going to be our h theta of x, our hypothesis function. So what this is, Neil, is this is an equation, right, that models price. That's what this does. And we want to guess and we want to find the values of theta so that this equation can accurately output the true price given a value that it's never seen before. That's what it's doing. That is what theta is. Theta is a parameter. It's a parameter. It's something we want to change, right? We want to change it. It's a coefficient. Imagine it as a coefficient in an equation. You have your traditional quadratic equation, which is ax squared plus bx plus c, right? Imagine that. What theta is the equivalent of a, b, and c. We want to model this.
Oh, okay.
That's all it is. It's your coefficients. And these coefficients decide on how your function looks like.
So you're going to model A, B, C to make the value to make the desired y result.
Yes, that's what we want.
Okay, we want the desired.
Yes,
y
we're
result.
fitting, in essence, we're fitting a line to a set of data. But this is obviously not going to be a linear. Actually, yes, this will be linear. But we don't know. It could be this, you know.
Well, yeah, if it's that.
But when we don't know what x power is, how do we? We have to figure out the x power as well, no?
Yeah, well, we have to come up with, and normally we already know the hypothesis function for a set of data because there are certain rules for it. You don't exactly need this for this because, well, this kind of like cuts that out. But you could just imagine this as this equation and just continue thinking it linearly, right? Because we're not going to think of it in crazy, I'll show you tomorrow when we do with multivariable, I'll show you actually the proof and for how we work with squareds and stuff. But for now, just imagine it as some linear equation, okay? This is going to be some linear equation, okay?
Okay. Yes.
I think it's going to be a linear equation. Don't take my word for it. Please, Stanford, don't sue my ass. This might actually be higher order polynomial, but whatever, doesn't matter. Just accept it, right? Now, we're going to be left with this theta. This is the parameters we want to find, and we can take these numbers, substitute it back into our equation, and when it... Is it stop recording? Is it recording?
No, it's still recording.
Okay. When we substitute these thetas back into our equations, and then we can now calculate price given these parameters. So let's say you have a bedroom, a house that is, I don't know, 900 square feet. Your bedroom, it's got 5 bedrooms, it's got 3 floors, and it's 20 years old. What will the price be? Now we can model the price.
Yeah, okay.
Now we know, given data that we've never done, this is machine learning. This is it. This is the learning algorithm for our regression, which is actually pretty cool, right? This is our linear regression / polynomial regression algorithm. Now, let's see, what else did I want to show you?
Are we supposed to figure theta out?
The computer figures data.
Yeah, we
Okay.
could probably, but it takes.
So-
Oh no, we can do it. It's not that difficult, but again, it's just a waste of time. Okay, now, Senor Young, your attention. Okay, so I'm going to show you now a matrix that is uninvertible. And I'm not going to actually write the matrix because it's a pain, it's massive. But magic 84. To my knowledge, the magic 84 is uninvertible. We can actually find that out. Give me a second. Make sure that's true. I don't want to give you false information.
Wait,
There are-
uninvertible doesn't mean like the unders or whatever that
Yes,
is.
it means that the determinant is 0. That means when you're multiplying by 1 over the determinant, you're going to get 1 over 0.
So AC minus BC equals 0?
Yes, that's what we're going to end up. So if we do the inv of...
The other one is 1, 2, 3, 4, 5, 6, 7, 8, 9. The one you
Yes,
say.
this is an indefinite, sorry, yeah, this is true. Magic 84 is uninvertible. So this is what we call, this is called a, what's it called? A degenerate.
What does magic do?
I'll show you.
Matrix is 84 by 84 with some special values.
Yes, it's going to be an 84 by 84 matrix that each column, row, and diagonal adds up to the same number.
Oh, okay.
Yeah, it's a great way of actually making matrices really quickly so that I don't have to think of generating my own. I could generate a random number generator and do that, but this is what we call a degenerate matrix. I know, an amazing name, trust me. Honestly, the degenerate, it's pointless, it's retarded. This is going to end up on YouTube, I need to edit that out. Demonetization, here you come. Wow, that was utterly awful singing. Anyway,
Just get a bleeper or something.
I need a bleeper, that's
Yeah.
sure. Now, we have a degenerate here. Now, this degenerate matrix is, this means essentially we can't take its inverse. Its inverse is indefinite, and if I show you on octave, you will see, I don't think you can read, but it just says infinite. Because we're multiplying by, in essence, infinity, right? So it has no inverse. Now, what are we going to do if our matrix, let's say our X matrix, our design matrix, right, X, turns out to be a magic 84 matrix? It could happen. There is some possibility that it, of course there are technically an infinite number of uninvertible matrices that could be there. There are loads. So what happens if it's something like this? Because then I can't take this. Or it doesn't necessarily need to be that X is uninvertible. It just needs to be that X transpose times X is uninvertible, right? So if X transpose times X, X transpose X is uninvertible, so it's degenerate. What do we do? Because then we're going to be stuck in a position, well, I can't take the inverse of that. Well, then I'm just going to be left with infinity. So machine learning can be done. But there are ways around this. And we're going to show you a way around this using something called the Moore-Penrose matrix. Pseudo-inverse matrix. Okay. Now, this is a topic of extremely high-level mathematics and is some of the coolest stuff that exists in vector
Can you
calculus.
like add 0, 0, 0 under it?
No. You will see. You will see.
I mean, 0 size, 0 bedroom. That's of course 0 primes.
Maybe, but don't do that, right?
With 0 bedrooms though.
You see,
Wouldn't be able-
also there are ways of avoiding ending up in a decrepit state, in a degenerate state to begin with. Let me turn the camera to the other side. There we go. Now, there are ways of avoiding coming to this stage to begin with, but what happens if we do end up in this stage? So, I'm going to, remember I said that this was important. This is important. Now, we're going to perform a function called the PIM function. PIM and in. Now, my knowledge of more Penrose pseudo-inverses are a little weak, right? Don't take my word completely, but we don't have to understand how exactly they function. They just have some interesting properties. Now, the in function is in essence this. It's in of x is equal to x to the minus, right? That is an inverse that allows us to carry out. Well, PIM is not that. I don't. Yes, or it technically means the pseudo-inverse. Now, this isn't really the true inverse of this, but it allows us to take the inverse. If I do PIM,
It's like changing the numbers a bit.
I can't exactly explain it. It's far more complicated than I'm willing to use. But PIM of this will be something we can calculate. It's doing the pseudo-inverse of 84, even of magic 84. We're calculating the magic 84 here without having a matrix a matrix that is degenerate. So how can we do that? How is this possible? Now, first I have to some disclaimer here. I don't exactly understand it myself. I'm no linear algebra expert. But firstly, some history. PIM was three people who did it. It was Roger Penrose, who's one of the greatest physicists to ever live. Guy who just won the Nobel Prize for black holes. He also did this stuff for fun. It's named after Moore, who was a very famous American computer scientist. One of the most iconic. You've heard of Moore's law probably. Just like the number of transistors on something decreases. I don't know. It's quite famous. And then there was this Swedish dude who also did this, but his name was too long and unpronounceable, so they decided to leave it out of the Moore-Penrose pseudo-inverse. Now, pseudo-inverse isn't the true inverse, it's that it's close enough. If I take the inverse, the pseudo-inverse, right? The pseudo-inverse of something that isn't degenerate, of some matrix X, right? It's going to be approx equal to the true inverse of N, right? It's going to be very close. In essence, if you use the round function in octave, it'll actually come the same.
Is it like putting like 0.00001 like at the bottom?
I don't exactly know the functions. But we can talk about this whole thing can be represented as this, x to the plus. Now that is in essence to my understanding, this is in essence the Moore-Penrose inverse, this entire section here, that allows us to do this inverse. How exactly that functions, again, it's beyond me. If you want to read to some of the Wikipedia page is incredibly complicated with derivations on how this works. But just accept that we can rewrite this equation, to my understanding, right?
Teacher recommends Wikipedia.
Wikipedia's amazing. I don't know what you people are all about. X plus, like that. Where x plus is this pseudo-inverse, right? We're performing a pseudo-inverse. Now again, we don't have to understand exactly how that functions.
What happens if you use the pseudo-inverse on a normal matrix?
Again, here, like I said, the pseudo-inverse on a non-degenerate matrix X will be approx the same value as the inverse of
So
that.
it's still slightly off.
It's to do with how rounding and stuff, because actually all the true numbers will be the same, but it's going to be zeros that are weird. You'll see, if we perform the function of this, I'll show you in the board in like a few minutes. I'll actually connect my computer to the board, because we're going to have to use it to...
Is that why that in octave they don't use zero, they do like zero?
Yes, if you use inverse, if you use the inverse function, right, if you use inv, octave will actually spit out zeros. But if you use pim, the pseudo-inverse is going to spit out numbers that are super small but very close to zero. So we could probably reverse engineer how it works, but it's beside the point. But I want to show you that there's some interesting properties of this x plus. The interesting property, to my understanding, is that x plus times x is going to be our identity matrix. So this is going to be an identity matrix, which means that this is an inverse in its own right. This is pseudo-inverse. So to my understanding, this is what pseudo-inverse is. Again, not an expert. This is just some reading that I've been doing. So what we've done is x plus times x is some identity matrix. Now I've built this in
That
octave.
makes sense, right?
I've built this in octave and it makes sense. However, when I get to where x to 3, right? A 3 it doesn't seem to be working.
X transpose times X inverse times X is identity.
Yeah, so it makes sense that we do that.
Yeah.
But then
No.
transpose times X inverse times transpose
This-
times again becomes identity again.
But you're forgetting something here. What I'm saying is all of this times x is the identity, not. I'm not saying that. I'm not saying that x to the inverse times x is the identity. That is true for non-degenerate.
That's true.
Yes,
Yeah.
for non-degenerate.
For degenerate ones, they times X.
This is true for degenerate matrices.
Okay. Only.
No,
only
I think
degenerate.
that's the reason mine didn't work when I was building it, is because I work with non-degenerate matrices. But using degenerate matrices and the pinv function, right? If I multiply, essentially what I'm saying is if I do x transpose times x, pinv, and then all of this, and pinv, and then multiply this by x the transpose, right? And all of that multiplied by x, going to be our identity matrix,
Oh, okay.
right? So I have a whatchamacallit. Yeah, that's going to be our identity matrix, given that I'm assuming that x is going to be some degenerate matrix to actually make this work. And again, this can all be represented as x plus. So if I write x plus on notation, understand that it's actually x transpose times x to the -1 power, or the pseudo inverse of that, times x transpose. Okay? That is our, this is stuff you will do if you go into like algorithmic computer science, not, oh dear, Mario is here.
Wait, it's locked?
Yeah, it's a lot.
Automatically locks.
Oh, it auto locks. Wow.
Hello, Mario. I know this is gonna look
Now
terrifying.
explain this all to us, Matthew.
Yes, this is gonna look terrifying, trust me. But don't worry about it. I have some graphical stuff to show you guys. But this pseudo-inverse stuff, this Penrose Moore pseudo-inverse is something, if you do algorithmic computer programming, if you go into just pure mathematics, this is something you'll do. That's more of my field rather than building websites and stuff, but I don't think you guys will go into it. But I think this is quite fascinating because it allows us, this is really just machine learning using math. That's all it is. Now, what I'm going to show you is, let's see, what are the benefits of this?
I'm not gonna let you
Now, what are some of the good things of this normal equation versus our traditional gradient descent algorithm, right? I'm going to show you some benefits and I'm going to show you some negatives. There are definitely negatives, but there are also huge benefits to this. So good morning, Leif. How you doing?
Nice, he's late leader.
Okay.
He's
Let's see.
It's fine.
Now, benefits of gradient descent, right? We had our gradient descent algorithm. So some benefits of that gradient descent algorithm is, well, let's see, not benefit, let's do some negatives, benefits. We'll talk about that, right? So one negative of gradient descent is that we have to choose a learning rate. Remember our alpha? Remember last time we failed in choosing alpha?
Yeah.
We should have chosen alpha, which was 0.01. We went for 1. We ended up,
It was completely off.
oh yeah, we ended up getting bigger values.
We just like,
Yeah. So the problem is with gradient descent, we have to choose an alpha, which is a problem because sometimes it's hard to choose an alpha and know what alpha you should have. And then you're going to have to need, remember for gradient descent, we're going to need many operations and many iterations. We have to go again and again and again. And that can be cost consuming, especially at a level where you don't have large data sets. Now, it might seem counterintuitive, but gradient descent works bigger with bigger data sets than this. And I'll explain why that is true. And the reason this is true is because this function takes a lot of time. Taking the inverse of something is time consuming, especially when you get larger and larger. Now, a modern computer could probably do a 10,000 by 10,000 matrix without a problem. Maybe 100,000 by 100,000, and it would be okay. But maybe after 100,000 by 100,000 matrix, it's going to become more efficient to just literally iterate through it, because the time that this will take will be significantly longer.
But that's
Because
only because of the inverse, right?
Yes, because of this inverse. This inverse function takes a while. And we have this transpose. Transposes don't take a lot of time. They can be done in constant time. Well, now here's, if you remember your complexities from when we first started the course, we're going to say that x inverse, the inverse of taking something, is represented by omega n cubic. So it grows through cubic time, right? So that means by increasing the dimension, in essence, right? We're going to be cubing the amount of time that it takes in the worst case scenario to perform this. And it's always going to be in the worst case scenario because math is kind of constant. It's not going to, suddenly you can solve it quicker, right? But it is going to be dependent on the type of matrix you put in. Some matrices are much easier to take the inverse of. And I'm going to show you now, before I show you how this functions, right, and connecting it up, I have some cool programs to show you. We're going to first talk about normal equations, whether they're good for, you don't need to choose a alpha. No alpha choosing. No cost function. No, you don't need to iterate. You don't have to do all of that. It's just one line of equation. You just shove your data in, poof, and you get out a couple seconds later, you spit out your parameter matrix. So the problem is, we have to compute this. This computation takes time, the Penrose inverse. And it's slow if n is large because, that computation is going to be, long. So it doesn't work for everything. So this can be a nightmare. So we're going to be working with both of them, but because my data sets are not going to be in the size of 10,000 or something. Yeah?
What if there is at the time is cubes, like?
Yes. This is a big O notation. So we're saying in the worst case scenario, by increasing the dimensions.
So if the time is between 1 and 0, then it becomes smaller?
Oh, I see.
I see what your point is. I think it will calculate it as a fraction of the total time of like a fraction of 1 rather than as. I know what you mean.
Yeah.
I don't.
Because then the effect will be different depending on the start.
I guess you can say that's why it's more efficient when it's smaller, but that still doesn't.
Yeah, that is true. It is quicker when it's smaller, and then when it gets bigger than 1, But it isn't time we're cubing. It's going to be, we're cubing our n value. Our n value, because we can never have an n value less than 1. Because our dimensions can only be one integer. These are integer dimensions. So we cannot get something lower than 1. It has to be 1 or 2 or 3 or 4. And that, so if it's a 4 dimension, 4 times 4 to the 3, which is what, 64, yeah? 4 to the 3, 64.
4 times 64.
Yeah, 64. So we're going to have like 64 somethings, units of time. Now, this is not going to be seconds, of course. It's going to be nanoseconds, microseconds. And actually, I'm going to prove that to you today. What I did is I've built this little script here. This is a timer script. So what this is going to do is this is going to calculate the inverse of a magic n matrix. And then I'm going to increase the value of n by 1 through each operation, so that we're going to start with 1, 2, 3, 4, 5, and we're going to get bigger numbers. And then I've created a little timer here. So a tick, don't get me wrong, this is called the tick-tock function. Now, of course it is tick. Talk. Now, what I did is I create a little timer here that's going to record the amount of elapsed time and then going to add it to some empty matrix X, and then it's going to plot these times versus the size of n, and then you're going to see how much time it takes versus how large the n value is, right? So if we run this, it's going to take a while.
It takes about 2 to 3 minutes to perform, so we're just going to leave it here. Yeah, it's a problem. We're taking the inverse, right? What's this line? 1 by 1. It varies. It goes from being a 1 by 1 to a 2 by 2 to a 3 by 3 to a 4 by 4.
Also, what this thing does is it also here, don't worry, it runs in the background. What this thing does is actually calculate both the inverse, normal inverse, and the Penrose pseudo-inverse.
For each of them?
For each of them, yes. And you're going to get 2 graphs. You're going to a graph with 2 lines, and you'll see the why this thing actually functions. You're not going to see the spikes.
So when it hits 84, it prints out the matrix and also the inf thing.
It just prints out the inverse.
The magic ones on the one and not for the other, right?
You'll see. But give it a second, and you'll see. This prints out the inverse. These are the inverses of the matrices.
The reason it's doing this is also because it's doing the other, the pseudo-inverse. That's why it takes a while. So we're going to see the 84 twice? Yes. No, you won't, because the pseudo-inverse will give a...
Look at the graph. Boom. We got 2 graphs here.
I wonder
You
which
have
ones
3
Oh, I see this.
spikes.
So these are actually you got more. These are all undetermined. These are all degenerate matrices. Now that red line, thin red line here is the Penrose inverse.
84 is much bigger than the rest.
Notice how the pseudo-inverse does function for 84. So you see that there is no spike. So they take about the same time. There are spikes up, but that's just because if you do something in a background, you can take longer time because it's taking computational power. So this is time here in seconds. So to find the inverse of a 100 by 100 matrix, it takes nearly 5 seconds to do.
Jeez, it goes. Yeah, I see what you mean exponentially.
Yeah.
Can
So
hear this computer fine offended.
okay, and I mean there are other things to show you, but I think I'll show you during chemistry instead because they're pretty cool.
Chemistry.
Yes.
Middle of chemistry.
Well, I'll end it here. Bye. So that's the video, I guess. I don't really have an outro or anything else to say, so hope you enjoyed.